I'm going to start here in presentation mode and talk a little bit about what I'm going to do. I'm going to show you several workflows for solving problems, teaching, and exploring physical problems. And this is kind of what I do for a living, all these things. And Wolfram language is kind of my go-to. The demonstrations I'm going to show you today are designed for people who have familiarity. And so you'll see some things today. If you are a beginning user, you'll see some things that may be unfamiliar. Intermediate users should be able to follow everything I do. So I have 4 examples. The first one is I picked an example where everyone who's taken an introductory physics class probably will have some idea of what I'm going to do. And I'm just going to take you through a workflow. And the notebook I'm going to work on, I've published on the cloud, just like Kelvin just talked about. And so if you want to download that notebook, you can grab that one right there. So that's the first example I'm going to do. I have 4 examples. The second example is just a mini lecture on calculating the band structure from a 1D periodic potential. So this is known as the Kronig-Penney model. It involves solving the Schrodinger equation using Bloch's theorem. Okay, so that might be a little bit specialized. The third one is I'm going to show you some examples of using finite elements. Wolfram language now has a fairly extensive finite element package. And I'll show you an example of usage to look at fracture conditions. And my fourth example is coding up your own molecular dynamics code. Okay, so I have all 4 of these examples. It's unlikely that I'm going to be able to get through all of these. And so what I'm going to do is I'm going to put all of these notebooks into the browser, into the chat window here. I'll give you the next one here. And finally, this one here. Okay, so there we go. So it's unlikely that I'm going to be able to get through everything. And that's fine, right? I want to start with the simplest example that I can, a nonlinear oscillator. If I have some time left after I finish that, then I'll let you guys vote for the next example. That is either this problem in solid state physics, this problem in mechanical engineering, or this problem in many different fields. Okay. All right, so I'll have 2 different things, workflows and mini lectures. The workflows will be artificial. I'll be copying and pasting code. And I have to say that it may seem like something is happening in a linear program fashion. That's hardly the case when I work. When I work, I make a lot of mistakes, I back up, I fix things. And so what you're seeing is artificial. And so don't be under the impression that you have to code the way that I'm showing you this particular workflow. And finally, I'm going to go pretty fast. The best way to slow me down is by asking questions. Okay, for the mini lectures, some of you may not be familiar with the physics, and I'll try to give a brief background to those of you who may not know the physics. Okay, so let me start sharing my first topic, and that is going to be this one. Okay. Okay, so you should be able to see my screen, and just somebody type into the chat window that you can see it if you can. And can you tell me whether it is large enough for you to see? Okay, great. Okay, so the problem I want to solve is the following, right? So I've made this little animation, and what I want to do is talk about how one might go about doing this problem. Now, what's nice about this animation is most of you already understand exactly what I'm doing, right? What I have here is a potential that has this very large repulsive term. I'm plotting a potential versus a separation, right? So I have my axis labeled down here. I'm going to make my magnification just a little bit smaller here so we can see all of the screen. And what we see is this oscillation around the bottom of the system. So clearly, I'm doing something like solving Newton's equations for this problem. We can see the nature of the nonlinearity. The system tends to spend more time away from its equilibrium point than it does at a small separation. And so what I'm going to show you today is how to work out this kind of problem, first symbolically, and then doing something like numerical analysis of the same problem. Okay, so I'm going to stop this animation. It's not a good idea to leave dynamic objects running while you're doing other things. Okay, so I want to tell you a bit about my workflow. So the first thing I'm going to do is start with this potential and show you how to non-dimensionalize the Lennard-Jones potential. It'll be a good example of using solve and then back substituting with rules. I'm going to try to solve F equals ma for this nonlinear potential or non-harmonic potential sitting up here. I'm going to find that I can't solve it symbolically. And so what I'm going to do is do an approximation to that problem and extract the characteristic frequency. I'm going to use that characteristic frequency as a time unit to non-dimensionalize this second order ordinary differential equation. And then I'm going to solve that numerical problem for the Lennard-Jones potential. And then I'll use the solution to do something interesting, right? So that's my job. And I'm going to show you the workflow I'm going to use to do that. Okay, so here's the form of the Lennard-Jones potential that, that is generally used, right? Something like this. This is my repulsive term, and then B gives me the magnitude of my attractive term. And I'm gonna hit Shift Enter. You can see that it turned from blue to black, meaning that I have this term. Okay, so I wanna turn this into a form which is a little bit easier to read. And so I'm gonna type in here the conditions that the system is at a minimum, right? So here I'm gonna say 0 is equal to the derivative of my potential with respect to R. And if I evaluate that at the minimum, it's gonna give me a 0. And then the value at the minimum is just taking my potential, using this rule saying if R is sitting at the minimum value, then the minimum of the potential is going to be E min. Okay, so I have these two equations, and I can solve these two equations for A and B. So I'm going to do that right here. So now oops, little window problem there. So now I have a solution for A and B sitting here. And I can take that and I can re-express my potential in terms of that solution. Okay, so what I'm going to do now is take these solutions. This is a list of one set of rules for solutions. I'm going to back substitute with those solutions. And I have a form of the potential, which is now in something which makes a bit more sense. I could simplify this expression, and that will probably factor out some terms. And I can see the form of this expression in terms of quantities that are a bit more useful. Okay, so I'm going to continue to non-dimensionalize this. And what I'm going to say is that I'm going to set R equal to a non-dimensional quantity multiplied by R min. So when rho is equal to 1, R is the separation is equal to R min. Okay, and then what I'm going to do is I'm going to take my potential and just divide by E min, and I have this very simple form of my potential, which I can now plot and look at the form of my potential, and we see, yes, when R is equal to R min, which is this 1, is sitting at the minimum, which is equal to -1. Personally, I don't like the default plots in the system, so I often add a lot of options to my plot. And I've done this nice little feature of iconizing the plot stuff. So there's a little sequence of 7 commands hiding in here. And I'll just go ahead and evaluate that plot. And I put a little extra graphics on there to help your eyes see where the minimum is with respect to 1 and where the minimum in the energy is with respect to -1. Okay, so let's go try to solve F equals ma. Okay, so the first thing we have to do is turn R, just remind you what this term looks like. Right, so we have this R in terms of its natural variables. The first thing we have to do is make R a time-dependent quantity. So I'm going to replace R with R of time. Okay, so that's now my potential as a function of time. If I want to calculate the force on this system, then if I have a potential, all I need to do is take the derivative of my potential with respect to R of t, and then I put a minus sign in front of it and I get my force. So that's the force I'm going to put into F equals ma. So here's F equals ma, right? Mass times acceleration is this term right here. And then I can do Newton's equation sitting down here. So here is my Newton's equation. Okay, so that's what I need to solve. Okay, so we might just try to use a differential equation symbolic solver, cross our fingers, and hope that it might have a symbolic solution. All right, so let's try it. So here we go. We're going to try to solve this differential equation. And one thing I want to call your attention to is that equations have the form of this double equal sign. This means logically equals this. It doesn't mean set 0 equal to this, which would be something that Mathematica would complain about. Okay, so let's try to solve it. So I have my equation. I want to solve it in terms of R of t. That's my variable, and this is my dependent variable. And so I'm going to try to solve it. This may take a little while to solve. You can see that it's still running, sitting up here. And in a minute, it's going to come back. It's still trying to solve. And it comes back with something that it claims is a solution. And in fact, it is a solution. It's just not a solution that I can really do much with, right? I don't really know how to solve this Apple F1 special function for R of t, but if I could, then I could use this equation. Let's suppose that I wanted to do something like add some initial conditions to this and hope that it might be able to find a solution for a special case. So what I'm going to say is solve Newton's equation, also add the conditions that R at time equals 0 is equal to 1, and that the speed at time equals 0 is equal to 0, and try to solve for R and the dependent variable t. I've sent it off to start trying to calculate this, and it will come back in a minute, and it will say, the general solution contains implicit solutions, which is what we had up here. These solutions will be ignored. And so dsolve is just bailing out and says, we can't do it, okay? So we can't find a useful closed form solution. So what do? Right? So what we're gonna do is solve something else. And we're gonna use that solution to something else as a way of sneaking our way into a numerical solution. And you'll understand what I mean by sneaking our way into a numerical solution in a second. Okay, so let's find the second order approximation. So I'm just going to do Taylor series. I'll remind you what this quantity looks like right here. Right, so I'm now working on using this form of the Leonard-Jones potential. I'm going to look at the series approximation. I'm going to expand that term around 1 up to second order. Okay, so this is the energy when rho is equal to 1. There's no force when it's sitting at its minimum, which is equal to 1 sitting here. And this is the quadratic approximation to the curve. And then there's something here, which is Mathematica telling me that I still am doing an approximation to the system. It's saying that, yes, there are terms around there that are of order rho minus 1 cubed. Okay, so if I want to do a subsequent calculation on that, I have to get rid of this order of aspect. And so what I'm going to do is exactly the same thing. And I'm going to say, take the normal form of this object. So I have this object sitting here, which I can go ahead and plot. So I have my original potential, I have my parabolic approximation, and here's the plot sitting here. So here's our parabola. We're going to be able to solve this differential equation associated with this harmonic oscillator. And then the problem that we really want to solve is the problem that is this blue line that's sitting here. Okay, so let's go solve the problem that we can. Okay, so what I'm going to do is write down an approximate Lennard-Jones potential. So I'm taking that original form, right? So it's in terms of these physical constants, R min and E min. It has this R of t sitting in it. It's going to be handy here to replace R of t with just the displacement around the origin. So what I'm doing is I'm saying R of t is going to be a displacement around R min. Just kind of will make the form of the solutions a bit cleaner. I'm going to evaluate that, and I'm going to look at the chat window for a second and see if there are any questions or requests to go a bit more slowly. Okay, then I'll keep going. All right, so the next step is we want to find out what the force is to this for this particular potential. So I'm going to take the derivative of our approximate potential with respect to this displacement parameter. We now have a term which is linear in our displacement. This is like K, this E min over R min squared, and this is like delta X in a spring equation. So if we want to solve the approximation problem, we can now just try solving. I'm going to set up Newton's equation. This is the approximate Newton's equation. This is going to be MA, and then I'm going to subtract off the force here. So this is going to be the right-hand side of Newton's equation. So when this thing is equal to 0, I'm going to be solving Newton's equation. Okay, so let's do that in the next step. And so I'm going to solve this differential equation in terms of delta R. And all of you pretty much know what the solution was going to look like ahead of time. Okay. What I really wanted to show here was the nature of the workflow and how I'm working symbolically and not numerically. Okay. All right, so that's a solution. We get two constants of integration, right? So there's this C1 and C2. We haven't specified initial conditions in our set of equations. If we did, those initial conditions would go away. So just to prove that, what I'm going to do is add some initial conditions. So I'm going to say delta R of 0 is going to be equal to 1. Don't forget the double equal sign when you do this. Otherwise, you often have to resort to quitting the kernel. At least that turns out to be the most effective way to do it. And then I'm going to say that the derivative of delta R with respect to 0 is equal to 0. Right? So I've got a system with no initial velocity and an initial displacement, and then it finds a particular solution. Okay. If you don't like having this rule here, there's another way to do this, where if you just want what the solution looks like, you can say, yes, just tell me what the value of that solution is. And so that's something that's relatively new in Mathematica. Okay, so let's see, let's move on. We look at this and we notice from this equation here that this cosine times t is the characteristic angular frequency. And so we're picking up something about the fundamental solution that we can use when we switch to our numerical solution. Okay, so let's go just define it by I, right? So what I'm going to say is that this characteristic solution, right? So I'm just taking this guy. I could extract this term using Mathematica, but sometimes it's easier just to do the algebra in your head. By the way, when I use Mathematica, I don't use Mathematica as a replacement for thinking and learning the things that I already know. I consider it to be some kind of partnership, that some things that are easy for me to do turn out to be a little bit difficult to teach Mathematica to do, like extract that coefficient. And so don't be embarrassed about copying and pasting terms. Okay. All right, so that's my characteristic frequency. Right, so I've defined this term, and what I'm going to do is define my harmonic solution. here. Oops, didn't, oh, here we are. I didn't evaluate this one. So here's my harmonic solution in terms of an amplitude and an initial velocity being equal to 0. And I'm going to take this and simplify this where I have these terms. Now, oh, notice something here on this simplify. I'm seeing this square root of mass sitting here, and a square root of mass sitting here, a square root of E min sitting here, and a square root of E min sitting here. So technically what's happening is Mathematica is not allowing you to make mistakes. If mass happened to be negative, your harmonic oscillator would do something very odd, like run off to infinity. And so what this is doing is keeping you from making mistakes. Mathematica probably shouldn't know that this symbol or this string mass means something that should be greater than 0. So what I'm going to do is just add an assumption to this, so an assumptions, and I'm going to say that mass is greater than 0, and I'm going to say that E min is greater than 0. I simplify that and I get something that looks very simple. Okay, so that's something about simplify. Those of you who are new to the language, these things here are called options, and it's a way of affecting the behavior of a function like simplify. And simplify's result is something that should be fairly obvious from what I'm doing right now. Okay, all right, so what I'm going to do now is write down what the harmonic solution looks like. Oops. Okay, so it looks like this term, and what I've done here is I have non-dimensionalized the problem again by dividing the harmonic solution that I had up here by R min. And I said that the amplitude is just going to be proportional to R min. So I have this proportionality factor. And I'm going to replace time with a non-dimensional time and multiply it by a time unit, which is omega. Okay. So I have this as being my basic solution. So all the physics is buried in this particular solution. All right, so this plotting won't be very interesting, but it will give me a chance to show you how to do something interesting. Okay, so here's our solution, simple harmonic motion. And we can play with manipulate. I can change the size of the amplitude, and I can change the time. Let's see, I'll just stop this, and I can change the time by evaluating this manipulate. Okay, so how did I do this? Okay, so the first thing I did is I said, okay, I'm gonna let the local solution be this dp harmonic, and this with statement is a handy thing to wrap around manipulate. And I won't talk about why right now, but it turns out that many people who are just beginning will find that their manipulates are not working, and the solution is often that wrapping this around manipulate for things that are local to the manipulate will help. Okay, so I'm plotting the local solution for a time span that I've defined. And then to this plot argument, I've added something which is a graphics object. What I'm saying is that at a particular point in time, take my local solution and let tau go to time. Okay, and so what I have here is a point, which is in displacement versus time, and it's moving along the curve sitting here. This is pretty much what I did when I showed you the example at the beginning of the lecture, where I did the nonlinear oscillation for the system. All right, so how do we do that nonlinear oscillation? And I'm going to take a pause there and see if there's any questions or any requests to go a bit more slowly. Okay, how about faster? Anybody want me to go faster? Okay, all right. So here is Newton's equation. This is what we want to solve. And this is the full nonlinear version that we worked out before. Okay, so we prefer to do as few numerical solutions as possible. So each time we change the mass or the depth of the well, we don't want to rerun the solution. We just have a very large parameter space, and we don't need to do that. What we want to do, and this is kind of my work mode, is I always try to non-dimensionalize my problem and get rid of as many variables as I can in order to calculate something. Especially if we're going to be doing a numerical solution, generally you can't put symbolic quantities into a numerical solution. And so therefore everything has to be pretty much non-dimensional, or you have to force it in. Okay, so let's see. So we want to turn this into a non-dimensional equation, right? We could do it with pen and paper, the way that we all learned how to do it, or you could do it with code, or you could do it with a combination of both of them, and that's fine too. Okay. In the differential equation, right, to move from this t parameter to this tau parameter, we're going to have to introduce this transformation of variables. And so every time we take a derivative, a 1 over omega is going to come out, right? So if you're a beginner, it's probably easier to do this with pen and paper than trying to do what I'm going to do next, okay? And so what I'm going to do next is the following. And this, I think, will be perhaps somewhat confusing to a lot of you, but what I'm doing is using something in Mathematica which is called a pure function. And what I'm doing is taking R and I'm replacing R, which is expression like R of t, and I'm replacing this with a function which takes another argument. Okay, so let me show you what happens here. So I had this d rho of t, right? So R of t replaced this term here. And so finally, if I want to introduce my non-dimensionalization, I can do this in the next step, where I can turn my function d rho into something that's multiplying omega. And the derivatives will operate through automatically. Okay, so what I'm going to do now is introduce my tau term. So I'm going to let t go to tau of omega. And so tau is my dimensionless unit. And so I have this equation sitting here. And now this equation is fully non-dimensionalized. Okay, so what I'm going to do is I'm going to multiply both sides of my equation by R min over E min. So what I've done here is taken my equation, 0 equals. I've multiplied both sides by this. It hasn't done the simplification yet. And so what I'm going to do is ask it to simplify. Right, so it did some simplification sitting inside here, but it also says that I have to assume that that E min over R min is not equal to 0, and then that's my equation. So I'm going to add to my simplification some assumptions. And I'm going to say that E min is greater than 0, and I'm going to say my R min is greater than 0. So those are my physical assumptions. And what I get is now my numerical equation sitting here. If I take this guy and I say, notes here, I take this guy, so just take my whole object here. And what I'm going to do now is replace the omega, which appears in here, with my omega characteristic. So I think that's what I called it. Yep. And oh, I need to say omega goes to this characteristic value of omega. Okay, and so now I have one equation which represents my fully nonlinear equation. And I can now solve this thing numerically. Okay, so I have some of my simplification sitting here. So it looks like I've already written this out. And so this is now, I'll just keep this guy up here instead of doing that again. Okay. All right. So we're now ready to start solving this equation. And so I'm going to use a numerical solution. Okay, so a numerical solution. This. I'm now using a form of dsolve, which is going to do everything numerically. And for this to happen numerically, everything inside here, this equation, has to be able to evaluate numerically. So what I'm doing is I'm saying the displacement value rho at time equals 0 is 0.1, and the velocity is equal to 0. And because this is a numerical solution, I have to tell it how far I want to integrate my time-like variable. Okay, so that was my numerical solution. It's very fast, fairly fast. And I'm going to show you how to go ahead and use this. Okay, so I'm going to make a plot. I'm going to go back and use ndsolve value with this, so I don't have to do the replacement. So that one, ndsolve, gave me this replacement rule. And here I'm just going to ask for what is the solution. Right, so my solution is something called an interpolating function. And all an interpolating function is a very rapid lookup table for finding numerical values from an array of numbers. So I'm now going to plot this guy. This is a function that takes a value, so a solution. If I pick a value of t, which is, let's say, 5.2, it tells me what the solution looks like there. If I were to do the same thing for 21.2, what it's going to tell me is that I haven't integrated far enough in my original solution to get there. Okay, so here's how we use this. I'm now going to plot this function, just like any other function. It's a function of t out to 20, and that's what we get. All right, so we can see that here our initial displacement, I don't have the variables here. I have time sitting along here. I've labeled my axis so that it's clear how I'm non-dimensionalizing time in terms of my physical variables, and the same thing here in terms of displacement. Okay, let's make this one a little bit more interesting with the larger initial displacement. Let's take this to 0.3. And then I'll plot this new one for 0.3, and what we see is the solution is spending much less time closer to the, much less time with close separation and spending a much longer time at far separations. Okay, so let's do a quick comparison between this and the harmonic potential. So do this here. And so what we see is a quick visualization of what the difference is between doing this numerical solution and this harmonic approximation. Okay, and so there's a lot of things we could learn here, you know, kind of the nature of a system which has this asymmetric potential. One thing that we might see is this particle spends more time away from the other system. Let's see if we can extract that particular bit of information. So let's dig a little bit further and see if we can extract what the period is as a function of the initial conditions. Okay, so what I'm going to do is I'm going to introduce a kinetic energy. And so the kinetic energy is going to be normalized by this minimum in the potential. And then I'm going to say Vmax is somehow extracted from this maximum potential energy. Right? So this is just a way of scaling a Vmax. In this problem, I'm going to make the system be going towards shorter separation. So I'm going to pick the negative root. And this is going to be, oh, I don't like doing algebra. So this is going to be what Vmax is in terms of my non-dimensionalized initial kinetic energy. Okay, so let's write down a way of extracting a numerical solution. All right, so here is a way of making a function in Mathematica. The way this works is I'm going to name a new function, LJ solution, sitting here. I'm going to name this in terms of a pattern, and then this is something which says I'm going to delay the evaluation of everything in the right-hand side until I use it. And then I'm doing something else a little special here. What I'm doing is I'm saying, anytime that I've asked you to calculate this function, I want you to remember it by using this equal sign. So this is something called memoization that I'm putting into this particular problem. So I have my function, right? So how does one use this? I can just do LJ solution 0.7, and it comes back with my interpolating solution. And then the next time I would want to evaluate this for the same quantity, I don't, it doesn't need to go do the work of finding a numerical solution here. This isn't, the work here isn't too onerous, but here it's not a bad idea to exchange memory for time. Okay, so let's just make a widget to plot our results. And it's going to be this. So here is my widget. And I need to make this a little bit smaller so we can see everything. Okay, so what I've done is plotted a whole lot of solutions with different values of kinetic energy, right? And so what I'm going to do is go pick out something with a larger kinetic energy. And I can see of all my solutions, kind of which one I'm picking out. I'll pick a larger kinetic energy, and the period is getting longer and longer. I'll pick an even larger kinetic energy. And then at some point, if the initial velocity is so large, this goes so far down in the repulsive part of the potential that it just kicks this atom out of this kind of bound pair. Okay, all right, so that is an interesting question. How does the period depend on the initial velocity? Okay, so let's go see if we can go do that. All right, so there's something called when event. I need to make this a little bigger for you to see. And what I'm going to do is I'm going to say, okay, when d rho of tau is back at 0, so back at 0 displacement, and the velocity is negative, and I'll tell you why that's the case, I want you to keep track of what time that happened, and then I want you to stop the integration. Okay, so this is how I'm going to code this up. I'll go through this code a few steps at a time. And it's just a simple addition to our previous function. Our previous function pretty much just did this. And what I've done is added, sorry, it was this part here, sitting here. This is my dimensionless max kinetic energy. And I'm going to look for this particular event. And when this event occurs, I want it to stop integrating. And then when it stops integrating, I'm going to throw away the entire solution. And then I'm just going to return what that period was. Right? So I don't really care about what the solution is. I only care about when it stopped integrating. That is, when it matched that particular condition. Right, so here's an example of how we would call it, LJ period. And we might want to know what the period is for a kinetic energy, relative kinetic energy of 0.87. And it tells me my period is this. It may be interesting to look at the period for a very small displacement. And that looks very much like 2 pi. And so that makes me feel pretty comfortable that in my normalized solution, system which can be approximated by the harmonic approximation is giving me a period of 2 pi. And so that makes me feel pretty good that what I've coded is correct. Okay? Another way to feel good about what you've coded is correct is to go visualize it. And so let's go do that now. Okay, so I'm going to plot the result of looking at the the period as a function of the kinetic energy, and I'm going to plot that period from 0 kinetic energy up to something which is about 1. Okay, so we went and plotted this, and what we see is that, well, this isn't formatted very well. What we see is that the period starts around 2 pi for initial kinetic energies, which are around 0. And then as the kinetic energy approaches 1, the system diverges to an infinite period of oscillation. Let's just see what's going on here by uniconizing this. And let's reduce the plot range to something like 0 to, I don't know, 30 pi, just guessing. Okay, that's probably a little nicer, showing the divergence. Okay, so I now understand this problem. I might want to think about why this thing is diverging at a maximum kinetic energy approaching 1. Well, I remember that I normalized this thing by the minimum potential energy. So of course, if the system can't hold on to that maximum kinetic energy, of course the system is going to fly apart. And that's what we're seeing from this workflow. Okay, so that's an example of doing kind of a fairly complete version of a nonlinear harmonic oscillator. I'm going to pause there and see if you have any questions, and then I will move on to another demonstration, and that will go very quickly since we have 15 minutes left. Okay, any questions out there? Don't see any. Okay, so let's see. I'm going to let you guys vote for the next hold on just while I do some window washing there. Okay, so let me share my screen again. And just go to my entire desktop. And I will ask you guys if you have a preference, which of these 4 examples you would like me to start on, if there's any preferences. If not, if there's no preferences, then I'll let you download that, and we can spend the last 15 minutes chatting. Okay, I'm going to do the FEM one. That one will go pretty easily. Okay, so I'm going to share my screen and pick my FEM simulation. I just have to find that. I think this is it. Yep. Okay. All right. So there we are. And I'm just going to take you through a. Can you see my screen now? It's giving me a message. Okay. Can you see me wiggling the screen? Can you see me highlighting? Okay, great. All right, so I'm going to show you a quick example of how to use finite element. And what I'm going to do is show you an example of Griffith criteria. And Griffith criteria is the following. Suppose I had some kind of beam. I'm going to imagine this is some kind of elastic beam. I'm going to imagine bending the beam, and I'm going to compare the energy that's released by extending a defect like this little notch with the energy associated with moving the notch. That is, there may be some work involved with creating an extra notch. Okay, so all of this stuff is sitting in these packages. So when you see these needs like packages, what you're doing is you're saying that Mathematica, go load something. This is not unlike what happens in kind of Python libraries. Load things as you need them. Okay, so here's my workflow. I just drew a simple sketch on my iPad. Luca, can you see my highlighting now? Okay, so I'm going to return my share. And I thought that I had lost it. There we go. Okay, so we should be back at the screen now. Okay, so I was sharing a static window. Okay, so I was talking about these things where I want to load a package. I was talking about what Griffith criteria is. And Griffith criteria is the following. If I have a beam like this and I twist on the beam, let's say I pull it in this direction, I pull it in this direction, I push it in this direction, I'm going to be putting elastic energy into this beam. And then I'm going to use that elastic energy to drive the crack in this direction. So the system has to do work to create new interface sitting in front of this defect that I'm drawing. So here's my workflow. I just drew a little picture on my iPad. I went through and I wrote down where I wanted to put a bunch of little nodes. I'm going to create my own finite element mesh. And then symbols in my system. I want a beam, which is going to be L long and 1 high. Okay, so I just go and I define my coordinates, right? So I just define my crack lengths symbolically for this width statement. So I can go back and change this later. So I have all my coordinates. I'm going to go back and I'm going to define connections between those coordinates. So I'm just going to draw a bunch of lines. And with those coordinates and with those lines, and I'm surprised I'm not seeing line element sitting here, meaning that, I'm a bit surprised I'm not seeing that turning black. Let's see what happens. Okay, that worked. So it gave me something which is an element mesh. And an element mesh is a numerical grid, loosely speaking. It's a numerical grid on which I can solve finite difference problems or numerical equations. I'm going to show you kind of a very simple example here. It is, in fact, very powerful. You can solve kind of nonlinear fluid flow problems. Okay, so I'm going to take my boundary mesh, which is just the outside of this object sitting here, and I'm going to turn it into an element mesh, and I'm going to show what my element mesh looks like. Okay, so here's my beam. I put a little extra line in here, and you'll see why later, because I want a little straight section in my code. Here's my notch. This is not going to be very good for the problem that I have in mind. I'm going to take this beam and I'm going to bend it. And if I'm going to bend it, that means the stresses are going to change very rapidly in the region right around this notch. So what I'm going to want to do is refine my function according to whether the area of my triangle is very large or very small. So when this statement is true, right, so I want to refine in this region defined by this, keep on refining the triangles until the area comes under that particular value, right? If you're outside the area, then use a more coarse mesh, okay? So it's done the refining system. Notice up here, originally we had 639 elements. Now we're down to about 41,000 elements. Let's see what that looks like. And we have a very fine element mesh sitting down here, okay? So I could do a little better than this, but I'm not going to bother right here. This will be about fast enough. And so most of you who are familiar with finite elements, the question would be, well, why not just make it very fine every place? And so it's always going to be a trade-off between speed and accuracy in this particular calculations. Okay, we're going to want to solve a system of differential equations on this particular mesh. And this is the plane stress operator. So we see we've got a divergence term, which is sitting here. The divergence is operating on a gradient of a displacement field. And so we've got something which is like a tensor operation sitting on a displacement field. And we have in here 4 different terms, right? So there's my plane stress operator, right? So this is my first operator. Oh no, this is 1 for each coordinate. And so we have different derivatives. Okay, so these are this is the gradient of the strain, or the strain gradient term. Okay. All right, so what I want to do for this problem is I want to take the elastic modulus in my beam, and I want to make my elastic modulus large on one side and small on the other. So what I've done is defined a piecewise function for my elastic modulus. And so I can use that in my definition, and I can go make a calculation where the modulus in the beam changes very rapidly across the middle position that's sitting here. Um, Finite elements don't really like these kinds of discontinuities, and so it's often a good idea just to replace that step function with something that's pretty close to a step function. So I'm going to make a very shallow gradient associated with this sharp discontinuity. And I could clearly take this and make it more tight if I wanted to. Okay, so that's going to be what the elastic modulus of my beam looks like. On the upper part of my beam, this is the vertical position, the elastic modulus is going to be large. On the lower part of the beam, it's going to be soft. So I don't know, imagine taking steel and gluing it to some foam rubber, and then the steel is on the top side, and I'm going to bend that beam with the steel being on the outer radius. Okay, so what I'm going to do is I'm going to take that plane stress operator, which had a modulus function in it, and it had a Poisson's ratio sitting in it. And I'm going to replace that elastic modulus with this bimaterial modulus, which is a function of y. Okay, so now I have this elastic modulus sitting inside of my differential equation sitting here. Okay, so this is now modeling a particular material by putting in these material parameters. All right, the next step is I want to put in some boundary conditions, and I'm looking like I might run a little bit over. So I hope you don't mind if I'm 5 minutes over. What I'm going to do is I'm going to say my solutions, U and V, which is my displacement field. I'm going to say, take the length of my beam to be 10, and I'm going to twist the beam by 30 degrees. I'm going to solve this equation on this finite element mesh for the displacement field U and V. So that's what it's going to look like. I'm now solving this on roughly 41,000 elements, and I get two numerical functions for my displacement fields. So let's take a look and see what that looks like. I'm going to plot a vector plot on this mesh. And what we see is little arrows associated with how these are moving. This isn't a terribly good visualization. I think I might have a better one sitting here. And the arrows are much smaller. I would have to work on this a bit more, this particular visualization. We can plot the deformed mesh. And so what we see is the original mesh in the deformed state. So this is 30 degrees, this particular angle. Or I can plot just the deformed boundary and see how that looks, just to get a better sense of what's going on. Okay, let's go grab the stresses and strains. So the definition of the strain gradient is ux, uy. And then, so this is the gradient of a vector. So I get a matrix sitting up here. I'm going to define all of those derivatives, ux, uy, just do it explicitly. It's a little bit easier to do it this way. And I have my deformation gradient, which is sitting here, which is a matrix of interpolating functions. So if I want to know what the strain is, what I'm going to do is give it a point where I want to know the strain. I want to give it the deformation gradient, which is a system of functions, and it's going to go calculate what the strains are. So for example, if I want to know what the strain at point 1 and point 2 is, this is x and y. For that deformation gradient, I can calculate what the strain tensor is at that point. And if I want to know what just the shear strain is, I can pick off one of those terms from this matrix. So just to make it clear, it's often useful to plot things that are matrix-like with matrix forms. Okay, so if I want to plot the stress, I can take the stress, I can plot the displacement gradient. For the stress, I'm going to have to know what my modulus function is, and then I've just gone through and I've calculated the stresses from strains. that I've defined here in this function. So for example, the stress at a particular point is equal to this value. Transform, you see it like this. Okay, last few steps, I'll finish in 5 minutes. Now, if I want to calculate what the elastic energy density is at any one point, I just need to sum over all the stresses and strains over this matrix sum that's sitting here. Okay, and so what I've done is I've just defined how I'm going to do that. So stress multiplied by strain. And if I want to know what the elastic energy density is at a particular point, I get a single value. So if I integrate over my entire mesh, the elastic energy density, what I should get is the total elastic energy for the system that I've just integrated. And I now know the elastic energy density. Okay, so I can put this all together. Okay, so I'm going to do something where I'm going to make my elements. So I'm going to start with coordinates again. I'm going to make a function that takes beam length and notch length and twist as variables. And I'm just repeating everything that I've done before, but I'm putting it into a handy function. So I'm defining my finite element sitting here. I've made this into a mesh. I have refined my mesh sitting here. I found a particular set of solutions. I've evaluated the derivatives of those solutions, and I've calculated the total elastic energy. So this takes about 20 to 40 seconds to compute. And while this is computing, I'm going to pull up another screen and show you how I would use these results. So that's one elastic energy. So I'm going to show you an example of what I would do with those results and make a something that I might want to teach with. And I'm not finding that, so I'm going to have to open it directly here. There we go. All right, so I'm going to show you this final result, and I'm going to take just a few more minutes to do this. Share my screen again. I'll just show my entire desktop. Okay, so what I've done is taken the results that I got last time. So it was about 20 seconds per calculation. And I've decided that I want to save those results in a file so I can run them sometime later. Right? So I've saved the functions that I'm going to use, and then I've saved the data that I've calculated for a bunch of different cases. Okay, so I'm going to go grab all of that stuff. And I've done this for 2 different cases: a single notch that runs through this delaminated beam, and a notch that goes down, hits this interface, and begins to delaminate in these 2 directions. Okay, so I've built this little interaction. And so what we're going to see here is plotted on here is the total energy of the system. So what I'm going to do is I'm going to take the system and I'm going to take this gamma term down to 0. So this is the total elastic energy stored in the system. If I add a term associated with the work associated with creating that little defect, that's this term sitting here. Okay. And so what this tells you is that the system, if I begin to bend it, right, and so now I'm looking at a twist angle of 30. If I take the system and bend it to a twist angle of 30, initially I have to initiate the crack. So this goes up a little bit, but as soon as the crack starts running past this point, it will arrest at that particular point. So what we'd have is a beam that looks something like this with a particular notch. So let's see, I'm going to take my little crack, I'm going to move it to a particular point, and we get a picture here of if I had the beam with those elastic properties and this amount of work associated with moving the crack, this would be the final state of my crack. And so this is a fairly detailed calculation. I went through it in roughly 15 minutes, but I was able to teach you something about how kind of linear elastic fracture mechanics works in these particular systems. Right? So here's exactly the same thing for this notched beam. So I take this, I take my work term down to 0, and what we can see is that this notch length has the stable value, which is sitting right about here. Okay, so that's what the stable notch looks like. So that's it.